Today we're going to prepare potassium perchlorate, a powerful oxidizing agent. We're going to do this by thermally decomposing potassium chlorate. It's worth noting that you can do this reaction using sodium chlorate instead, which may be easier to obtain. You can't then add a soluble potassium salt later on in the preparation to get crystals of the relatively insoluble potassium perchlorate salt. We're starting off with 30 grams of potassium chlorate crystals, as you can see here. We're going to use a 50 ml porcelain crucible to perform the reaction in. It's important that you don't use anything that could oxidize. Molten chlorates use oxidizing agents, and we suspect metal containers might not be suitable. Try on a very small scale if you must use these. And make sure your crucible is spotlessly clean, especially with no organic residue. Let's get going. First we'll place the potassium chlorate into the crucible. And we've set this up over our gas burner using a stand and clamp. We want to be able to carefully adjust the height of the crucible in order to control the temperature. We're using our oldest clamp, which has no foam or rubber material on it. Just plain metal, so it will hold up to the temperature okay. And we're going to start off heating with the lid loosely placed over the top here. It doesn't quite fit with the clamp, but that's okay. And don't forget one of these. Very useful for removing the lid, as it's going to get very hot. We're all ready, so it's time for blast off. This shouldn't need strong heating. The idea is to get the solid to melt and then carefully heat above this temperature to get the reaction to take place. As the crystals are heated, they make cracking sound, like miniature explosions. This is called decrepitation, and it's the reason we've got the lid on to begin with. Pretty soon the solid starts to melt, and the cracking sounds die down. Once the solid has completely melted, you can remove the lid. Now we're going to keep on heating, and we should start to see some decomposition of the chlorate with the formation of oxygen gas. This is a side reaction, but it's an indication that we're in the right temperature zone for the disproportionation into perchlorate to occur. After a few minutes of heating, some bubbling like effervescence starts to appear in the liquid. And this gradually grows stronger. Keep on heating. If you need to, move the crucible up very slightly so that the bubbling is not too strong. The process takes about 40 to 45 minutes to complete. First you'll start to see a crust of white solid appearing in the crucible. This will get larger, and then you'll notice that the liquid bubbling at the bottom of the crucible is actually mostly solid, as you can see here. At this point, remove from the heat and allow to cool. Here's what was left in the crucible. Around 26 grams of a white solid, which shrinks slightly as it cools, making it easy to remove from the crucible. This is a mixture of potassium chloride, some unreacted potassium chlorate, and our product potassium perchlorate. We've got the 250 ml conical flask set up on a hot plate stirrer and with a large magnetic stir bar. Here's 100 ml of hot water. This goes into the flask. And with stirring on vigorously, we now add the white solid, which we've crushed up in order to help dissolve faster. Switch on the heat and get the mixture nice and hot. 100 ml of water should be enough to dissolve everything, but you'll need to get the water up to boiling point, and it will take quite a lot of stirring. This is looking good now. We're nearly at 100 degrees C and we've got everything dissolved. At this point switch off the heating and stir and allow the mixture to slowly cool down. Keep a thermometer in there so you can measure the temperature. Quite quickly you'll see white crystals forming in the solution. This is our product, potassium perchlorate, which is the least soluble salt in hot water. At about 60 degrees C most of this should have precipitated with a very small amount of potassium chlorate and none of the chloride. So we set out to filter off the crystals at 60 degrees C. We get them dry on the pump and then wash them with a small amount of cold water. Here's our product. Around 15 grams of pretty white crystals which look like tiny snowflakes. This is potassium perchlorate with a small amount of the chlorate as an impurity. This represents about a 60% yield on the starting potassium chlorate we used. Note that the filtrate still contains some of the product, and as it cools more crystals form. These contain a lot more impurities however, so it's a trade-off. The higher the temperature you filter at, the less yield you get, but the better quality of product you get. You could also concentrate this solution and recrystallize again. However, we decided against this given the work involved and given that we do have some nice perchlorate product to work with. Okay, let's do some tests with our product. First of all, here's a few crystals of potassium perchlorate. Let's add a few drops of concentrated hydrochloric acid. There's some smoke from the hydrochloric acid, a very faint yellow color, but no reaction. Let's do this again but using potassium chlorate, our starting material. There's a reaction, bubbling, a yellow color, and a choking aroma of chlorine gas produced as the hydrochloric acid is oxidized by the chlorate. Now we've got some perchlorate again. This time we're going to add concentrated sulfuric acid. There's a bit of smoke, but not much appears to happen again. So let's try this with chlorate, our starting material. A vigorous reaction and a yellow gas is produced. This is chlorine dioxide, which smells a bit like chlorine and is highly irritating, but perhaps a touch sweeter. It's also explosive, so don't attempt this on any sort of scale. The glowing bit of paper produces cracking sounds as the bubbles of gas explode. Okay, you could be forgiven for thinking that our product is very boring and not a good oxidizing agent. So we'll do one final test and we'll start this time using the starting material, potassium chlorate, and a little bit of red phosphorus. We've not crushed them up very finely as you can see. Okay, a little mix around, and we're ready for showtime. Here's a hot metal rod. So that's potassium chlorate. Works pretty well. Okay, now let's try again using our product potassium perchlorate. A small amount of red phosphorus. Again we're using coarse materials so it's not too violent. A hot metal rod. Doesn't work. The rod is definitely very hot, so this is interesting. The mixture is less sensitive. Let's use a more stringent approach. Yeah, that worked. This demonstrates an important point. Although they are in theory stronger oxidizing agents, perchlorates are more stable than chlorates. This is useful if you're building a solid rocket booster. You want power and stability. You need the fuel to ignite predictably at exactly the right time. We'll hold on to our little bit of potassium perchlorate and see if we can find a use for it. Generally, organic compounds and perchlorates are not a good combination, but who knows? Thanks for watching and stay tuned.